Hello there, and welcome to the Sleepy Thought Channel. Tonight we're drifting far beyond our own solar system into a universe filled with strange and extraordinary planets. Out there, worlds exist that defy almost everything we once believed about how planets should behave. There are blazing giants so close to their stars that their skies glow with vaporized metal. There are dark, wandering worlds with no sun at all, moving silently through the cold between the stars. And there are places where the very idea of land, sky, and ocean begins to break apart into something far more unfamiliar. With each new discovery, the universe reveals something unexpected, something that stretches the imagination just a little further. These distant planets are scattered across a cosmos far more diverse than we ever imagined. If you enjoy these gentle journeys, I invite you to subscribe, or share a thought below. It helps others find their way here to one sleepy soul at a time. But for now, all you need to do is relax. Let your shoulders soften, allow your eyes to grow heavy, and notice the day begin to gently fade away as we explore these strange and distant worlds together. Let's begin. There are worlds where iron may fall as rain at night. One of the strangest ideas in astronomy is that rain does not have to be water. On the exoplanet WASP 76b, the dayside is so hot, but iron can vaporize into the atmosphere. Powerful winds then sweep that iron vapor toward the night side, where temperatures drop enough for it to condense into droplets. In other words, the planet may have weather made from metal. Not everywhere, and not in the calm silver way the phrase suggests, but in an infernal cycle of heat, wind, and condensation, unlike anything on Earth. The world is locked to its star, which means one side faces daylight all the time, while the other remains in darkness. That permanent contrast helps drive the process. What makes this so gripping is that it sounds like fantasy, yet it emerges from real observations of a real planet. Even the word weather feels too gentle for something this extreme. Some planets are so hot metals can evaporate into the sky, far from being rare curiosities. Some giant planets live so close to their stars that ordinary ideas about weather begin to fail. On these worlds, the heat is not just fierce, it is transformational. Temperatures can climb high enough to rip apart molecules and turn metals into vapor, so iron, magnesium, and other heavy elements may drift through the atmosphere like ghostly gases. A rocky mountain could not survive there. It would soften, glow, and eventually become part of the air. These planets are often called ultra-hot Jupiters, though the name hardly prepares you for what they are. They race around the stars in blistering orbits and endure a constant flood of radiation. For astronomers, they are astonishing laboratories. By studying their glowing atmospheres, scientists can watch chemistry unfold under conditions no world in our solar system can match, and discover how much stranger a planet can be than anyone once expected. Some strange planets orbit two suns instead of one. For centuries, double sunsets belonged to myth and fiction. Then astronomy caught up. Some planets truly do circle two stars at once, tracing wide paths around stellar pairs that orbit each other. The first confirmed example to seize the public imagination was Kepler 16b, a world where two suns would hang in the sky together. It is hard to overstate how much this changed the feeling of the universe. A solar system no longer had to look like ours. It could be built around a partnership. Days, seasons, and shadows on such a world would be shaped by two moving sources of light, not one fixed sun. Even the sky would feel less predictable. These planets also proved something important about nature. Planet formation is tougher and more creative than we once thought. In a place where two stars are constantly tugging at surrounding material worlds, can still emerge and hold stable orbits for ages, quietly circling both suns together. Rogue planets wander through space with no star at all. Most planets belong to something. They orbit a star, keep to a family, and move through space as part of a system. Rogue planets break that picture completely. These are worlds that drift alone through the galaxy, untethered to any sun. Some may have formed around stars and then been flung away by gravitational chaos cast out. during violent encounters with larger planets or passing stars. Others may have formed in isolation from the start, more like failed stars than escaped planets. Either way, they wander through darkness on journeys that can last billions of years. At first glance, such a world seems hopelessly dead, but it may not be that simple. A thick atmosphere and leftover internal heat could keep some rogue planets warmer than expected, especially deep below the surface. That possibility makes them feel even stranger. A planet does not always need a sunrise to remain a world. Sometimes it can carry its own hidden story through the dark. One known world may have a glowing ocean of lava. 55. Concrete E is the sort of planet that makes Earth feel almost impossibly mild. It is a rocky world, not a gas giant, yet it orbits so close to its star that its surface may be covered in a vast ocean of molten rock. Imagine a horizon made not of water, but of liquid stone, glowing orange and red beneath a dark sky. This world is likely tidally locked, so one side receives intense stellar heating again and again, while the rest of the planet struggles to redistribute that energy. Astronomers have even found signs that it may hold an atmosphere rich in gases released from its hot interior. That matters because it suggests the planet is not just a dead cinder. It may still be geologically active, with magma gases and heat locked in a fierce exchange. This is not simply a hot rock. It may be a living furnace reshaping itself under a sun that never lets up. Some planets travel around their stars in less than one day. A year on Earth feels natural because it matches the rhythm of our seasons and lives. But some planets make a full orbit so fast that an entire year can pass in less than a single Earth day. These worlds cling so tightly to their stars that gravity keeps them in relentless motion, circling again and again at distances that would seem impossible to us. One lap in a year is over another, begins almost immediately. This changes everything about how such a planet exists. The star looms huge in the sky. Heat can become overwhelming. Tidal forces may lock one hemisphere into constant daylight. The atmosphere, if there is one, must cope with extremes that our solar system barely insert. What is so captivating here is the collapse of familiar scales on these worlds. The phrase "next year" loses all meaning. Time itself feels different when a planet races through its orbit faster than Earth spins through one ordinary day. There are planets so dark they reflect almost no starlight. We often imagine planets as bright spheres catching the light of their stars, but trust 2b shattered that expectation. This gas giant is one of the darkest known planets, reflecting so little light that it is darker than coal. It does not shine back its space in any familiar way. Instead, it seems to swallow starlight, almost completely, leaving only a faint red glow from its own heat. That darkness is not just eerie, it is scientifically thrilling. Something in the planet's atmosphere appears to absorb rather than reflect, even though the world is hot enough to glow. It suggests clouds' chemistry and light can behave in combinations that feel almost unnatural to us. A planet can be burning and still look black. That contradiction is part of what makes strange planets so addictive to think about. They do not simply offer new places. They force new meanings onto words we thought we understood, like dark day and sky. Some worlds may be covered by oceans deeper than Earth can imagine. Earth feels like a water world until you compare it with what may exist elsewhere. Some exoplanets could be wrapped in global oceans, hundreds or even thousands of miles deep, with no continents, no shorelines, and no familiar meeting place between land and sea. On such worlds, the descent would not end in a rocky seabed like ours. Pressure would rise to such extremes that water itself could transform into exotic forms of ice, even while temperatures remained high enough for liquid layers above. That means a planet could hold an ocean, then a buried shell of compressed ice, then rock far below. It is a beautiful and unsettling arrangement. These worlds might look calm from space blue and serene, yet their interiors could be stacked in layers, unlike anything on Earth. They widen the meaning of ocean beyond recognition. Sea does not have to mean beaches and tides. Sometimes it means a planet almost entirely claimed by water. One bizarre planet may be stretched into the shape of an egg. A planet named WASP-12b is so close to its star that gravity is pulling it out of shape. Instead of remaining nearly spherical, the planet appears stretched by enormous tidal forces into something more like an egg or a football. That alone is extraordinary, but the story gets stranger. The same gravitational strain is helping strip material from the planet drawing gas away toward the star and slowly tearing the world apart. So this is not merely a misshapen planet. It is a planet under visible stress, being distorted and consumed by the very star it orbits. Its year lasts just over a day, which tells you how brutally close it must be. We are used to thinking of planets as stable things settled into neat forms by gravity. This world shows the opposite. A planet can be deformed, heated, and eroded until it becomes something temporary and tragic, a place caught in the act of losing itself. Strange permits have changed what we thought a planet could be. Not long ago, planets seemed easy to picture. There were rocky worlds, giant worlds, moons, rings, and a neat solar system to measure everything against. Then exoplanet discoveries arrived and smashed that tidy picture apart. Astronomers found giant planets hugging their stars, worlds circling two suns, planets darker than coal planets, with lava surfaces and lonely wanderers with no star at all. The result was bigger than a list of oddities. It was a change in mindset. Our solar system stopped looking like a template and started looking like one example among countless possibilities. That shift may be the most astonishing discovery of all. The universe was not merely more crowded than we imagined, it was far less predictable. With more than 6,000 confirmed exoplanets already found and billions expected across the galaxy, the real lesson is humbling. Planetary nature is more inventive than human imagination first allowed, and it may still be only getting started. Some giant planets are puffier than candy floss, yet wider than Jupiter. A few exoplanets are so swollen and airy that they seem almost impossible. They are enormous in size, sometimes wider than Jupiter, yet their mass is astonishingly low. If you could place one in a giant enough ocean, it might float. That sounds playful, but the physics behind it is serious and strange. These worlds are called superpuffs, and they seem wrapped in vast envelopes of hydrogen and helium that stretch far from their cores. Their gravity is so weak at the outer edge that the atmosphere balloons outward, giving them a ghost-like bulk. Kepler-51b is one of the best-known examples of planet with the breadth of a gas giant and the density of spun sugar. These planets challenge formation models because they look fragile, inflated, and temporary. They seem less like solid worlds and more like drifting celestial mirages, huge in silhouette, yet barely holding themselves together. A few scorching worlds may have permanent day and permanent night. Some planets orbit so close to their stars that gravity has slowed their rotation until the same face always points inward. One side lives under a fixed sun that never sets, the other remains in endless darkness with no dawn and no memory of noon. This is not a rare poetic idea. It may be common among close orbiting exoplanets. The consequences are dramatic. The star-facing side can become hot enough to melt rock, while the far side may plunge into temperatures cold enough to freeze gases from the air. Between them lies a twilight zone, a narrow belt where conditions might be calmer, though still swept by violent winds, trying to balance the world's extremes. On Earth's sunrise and sunset shape how we feel time. On these planets, time is different. Light becomes geography. A person standing still would not wait for day to end. They would have to travel to escape it. Some planets may have skies filled with vaporized rock. On the hottest rocky exoplanets, the atmosphere may not be built from water vapor, nitrogen, or carbon dioxide in the way we instinctively imagine. Instead, it could be made from stone itself. When a world orbits close enough to its star surface, rock can heat until it melts and begins to evaporate. That creates an atmosphere of mineral vapor filled with ingredients like sodium silicon monoxide and other gases released from molten ground. Picture a planet where the sky is not above a landscape, but rising from it exhaled by the planet's own glowing crust. In some cases, this vapor may drift upward cool and then return as droplets or grains of condensed rock. It is an atmosphere born from the surface, being slowly turned into air. That idea rewrites something basic in the mind. We tend to separate land from sky. On these worlds, the land itself may become the sky. One distant world may be losing its atmosphere, like a comet. Some planets do not simply orbit their stars, they are being undone by them. There are worlds so intensely heated and blasted by radiation that gas streams away from them into space, forming long tails that resemble those of comets. One of the most striking cases is Gliese 4.3. 6b, where observations suggest hydrogen is escaping in a huge cloud, trailing behind the planet. It is a haunting image because a comet's tail feels natural to us, but a planet with one feels tragic and unstable. This is a world in the act of changing, perhaps shrinking over immense stretches of time as its star strips away layer after layer. The process is invisible to the eye, yet astronomers can detect it through the way the escaping gas absorbs starlight. A planet can be eroded by light itself. It makes every orbit feel less like a path and more like a slow surrender. There are planets where the wind may outrun the speed of sound. When astronomers talk about alien weather, they are not being casual. Some exoplanets may host wind so violent that they move faster than sound itself. These are not breezes or storms in any earthly sense. They are global rivers of gas, driven by the enormous temperature contrast between the side facing the star and the side turned away. In that constant struggle to move heat around the planet, the atmosphere can accelerate to extraordinary speeds. On certain hot Jupiters, scientists think these winds may screen through the upper atmosphere at several kilometers per second. That is fast enough to circle continents in hours, fast enough to turn weather into something close to planetary violence. The effect is not just dramatic. It also changes what astronomers see, shifting hot regions away from the point directly under the star. So even from like years away, these invisible winds leave fingerprints. A planet can reveal its storms without anyone ever touching its sky. Some avian worlds may have clouds made from sand or glass. Clouds sound comforting until you remember that clouds are simply what the local environment allows to condense. On Earth, that usually means water. On a much hotter planet, the raw materials can be utterly different. Some exoplanets may form clouds from silicate particles, the same broad family of materials that helps make sand rock and glass. High in the atmosphere, where temperatures and pressure reach the right balance, those substances may condense into fine mineral grains and drift like alien weather systems. Imagine looking up and knowing the clouds above are not wet, soft, or cool, but composed of tiny specks of rock. On certain worlds, these clouds may glow, scatter starlight in unusual colors, or help control how heat moves through the atmosphere. They make the familiar shape of a cloud feel newly strange. A cloud is not defined by softness. It is defined by suspension. Even powdered stone can float. When a world is strange enough, a few planets may have magma seas instead of oceans. Some rocky planets orbit so close to their stars that their surfaces may never fully solidify. Instead of continents, valleys, and seas of water, they may host vast pools of molten rocks spread across the dayside like glowing inland oceans. These magma seas are not just a surface detail, they could shape the entire behavior of the world. Liquid rock can absorb heat, circulate, release gases, and interact with whatever thin atmosphere exists above it. That means the boundary between geology and weather begins to blur. On a world like K2 1:41b, a person would not see waves breaking on the shore, but perhaps a horizon of moving fire. Some of these planets may even have rock vapor rising from the molten surface, then condensing elsewhere. The result is a planet that behaves less like a solid place and more like an active furnace. It is still a world, but one caught halfway between planet and eruption. Some worlds circle dead stars that should have destroyed them. When the star dies, it does not always do so peacefully. It swells, sheds its outer layers, and leaves behind a dense remnant such as a white dwarf or pulsar. That makes the discovery of planets around stellar corpses so astonishing. In many cases, those planets should have been consumed during the star's violent transformation. Yet some are still there. They either survived impossible odds or formed later from the debris left behind. Both options are remarkable. A planet that survives such an event has lived through the destruction of the very system that created it. A planet that forms afterward is stranger still, because it means planetary birth can happen in the ashes of stellar death. These are not ordinary solar systems, they're afterlives. They remind us that the story of a planet does not always begin in calm gas around a young star. Sometimes it continues after disaster, in a place where almost everything familiar should have ended. One planet may have formed from the remains of a shattered star. There is at least one famous exoplanet candidate that sounds almost mythic, a dense world that may have formed from the wreckage of a destroyed star. The planet around pulsar PSRJ 1719-1430. 8 is thought by some astronomers to be the carbon-rich remnant of a once larger companion star, stripped away until only its hardened core remained. If that interpretation is right, this is not merely a planet in the usual sense. It is a stellar remnant recast interplanetary scale. It may be packed with crystalline carbon under such extreme pressure that the phrase diamond world entered public imagination. Whether or not that image is fully accurate, the deeper truth is astonishing enough. A world may exist that was not assembled gently from dust in the young disk, but carved out of the death of a star by gravity, radiation, and time. Planets can arise from Earth, but also from ruin. Some planets may have no solid ground anywhere beneath their clouds. It is easy to picture landing on a planet, even a hostile one. Our imagination always searches for ground, but some planets deny that expectation completely. Gas giants and ice giants do not offer a true surface in the earthly sense. The visible clouds are only the beginning of a deep descent into thicker and thicker layers of atmosphere. Fluid and compressed matter fall through the clouds of such a world, and you would not strike a solid plain or mountain range. Instead, pressure and temperature would rise without mercy. Hydrogen might shift into exotic states. Chemistry would grow stranger with depth. The idea of down would survive, but the idea of floor would not. This matters because many exoplanets we discover are giants of exactly this kind. They are worlds without shorelines, without stone underfoot, without a place to stand. A planet does not have to be solid to be real. Sometimes it is a deep atmosphere all the way into mystery. There are worlds where a year lasts only a handful of hours. Some exoplanets orbit so breathtakingly close to their stars that their whole year can pass in less time than a film or an afternoon nap. These are the speed demons of planetary astronomy. They complete full orbits in only a few hours, racing around their stars on paths so tight that our own solar system offers no real comparison. On such a world, the star would dominate everything. It would hang huge in the sky, pouring out heat and tidal force with relentless intensity. The planet's orbit would not feel stately or cosmic. It would feel desperate, as if the world were clinging to the edge of destruction. These ultra-short period planets are especially fascinating because many are small and rocky, which means entire. Solid worlds can survive in places where older models said they should not. A year becomes almost meaningless there. The basic rhythm that defines planetary life on Earth is compressed into something furious, intimate, and astonishingly fast. Some planets travel around stars that are far older than the Sun. Our Sun is middle-aged by stellar standards. Yet some planets orbit stars that have been shining for far longer. That means there are worlds in the galaxy that may have existed while Earth was still assembling, or even before the Sun itself was born. One famous example is the planet around the star PSRB 162026, often nicknamed Methuselah, because the system may be more than 12 billion years old. To imagine a planet that ancient is to feel time expand in a new direction. This world may have seen the galaxy in a much earlier state, when heavy elements were rarer and the Milky Way itself was younger. Ancient planets matter because they test the timeline of planetary formation. They suggest that worlds began appearing very early in cosmic history. The universe may have been building planets for almost as long as it has had stars making our own. Worlds feel young late and wonderfully recent. A few strange worlds may glow from their own leftover heat. Not every planet shines only by borrowed light. Some young or massive worlds still carry enough leftover heat from their formation to glow in the infrared, radiating energy from deep inside themselves. This is one reason a few exoplanets have been photographed directly, because they are warm enough to stand out against the darkness. When viewed with the right instruments, it is a beautiful idea. A planet can still be warm from the violence of becoming gas, collapsing inward material crashing together, gravity squeezing the interior. All of that can leave behind a reservoir of heat that lingers for millions of years. In some cases, that glow tells astronomers more than reflected starlight ever could, revealing clues about the planet's atmosphere, age, and mass. These worlds do not look bright to human eyes, but they are not cold silhouettes either. They are embers of creation slowly cooling in the dark after their long and turbulent birth. Some planets may have hidden cores wrapped in vast mantles of ice. When we hear the word ice, we think of something brittle, pale, and cold enough to crack beneath a boot. Deep inside certain planets, ice may mean something far stranger. There are worlds that seem to sit between rocky planets and gas giants with dense interiors that could include a central core wrapped in enormous layers of high-pressure ice. This is not ice you could skate on under immense pressure. Water can lock into exotic crystal forms that do not exist naturally on Earth's surface. That means a planet may contain an internal architecture unlike anything familiar, with rock at the center, then layers of compressed water ice, then lighter material above some. Many Neptunes and ocean-rich planets may fall into this category. It changes how we picture a world from the inside out. A planet does not need a fiery mantle beneath its crust. Sometimes it's hidden. Middle may be a kingdom of crushed hot and alien ice. There are giant worlds that skim so close that stars distort them. Gravity is not just a force that keeps planets in orbit, but very close range, it can become a sculptor. Some giant exoplanets travel so near their stars that they raise tides on the star itself, tugging at the stellar surface, and helping distort the shape of both bodies. The effect is subtle from a distance that the consequences can be dramatic. The planet may be stretched, heated, and tormented by tides, while the star can brighten or shift in response to the constant pull. In these systems, the boundary between star and planet feels less tidy than it does at home. They are locked in a close gravitational dance, each affecting the other in visible ways. This is part of what makes hot Jupiter so extraordinary. They do not merely orbit, they interact. Their presence can change how their stars behave, proving that planets are not always passive companions. Sometimes a world is close enough to leave fingerprints on the sun it circles. Some permits may be tightly locked forever with one frozen face. Tidal locking does not always create a furnace on one side and a wasteland of darkness on the other. On planets farther from their stars, the locked night side could become a place of extraordinary cold, especially if the atmosphere is thin or absent. In that case, heat from the day side would not travel efficiently, and the hidden hemisphere might trap cold for ages. Gases could freeze onto the ground, frost might build in permanent darkness. A locked world like this would have two personalities written directly into its geography, one facing warmth and one collecting winter without end. This possibility matters, especially for planets around small red dwarf stars, where tidal locking is expected to be common. It means habitability is not simply a question of distance from the star. The rotation of the world matters too. A planet can set in the right general zone for liquid water and still hide one face in the cold that never releases it. Others may keep one side blistering hot and the other dim. Some tightly locked planets do not divide into hot and cold in a simple, balanced way. The star-facing side can become unimaginably hot, while the far side remains not fully frozen but dim or steer. and starved of energy. In between lies a world shaped by unevenness. A bright hemisphere may glow under relentless radiation with rock or cloud decks heated to extremes. The far side may not be a perfect ice ball if winds carry some warmth across, yet it could still remain a place of deep shadow and muted skies. That contrast is part of what makes such planets so gripping. They are not only physically divided, they are divided in mood. One side is exposed and overwhelmed, the other is hidden and restrained. Even if no life could survive there, the geography itself feels dramatic. A planet can become a map of imbalance with climate-like and atmosphere, all stretched between two radically different halves. Some alien skies may never know sunrise or sunset at all. On Earth, sunrise and sunset are among the deepest rhythms in life. They shape sleep migration weather and the emotional texture of the day. Yet some exoplanets may never experience either. If a world is tidally locked, then from most locations, the sky would be permanently fixed near the star-facing center. The sun would hang motionless overhead or slightly offset, never climbing and never falling on the dark side. The stars might remain unchanged night after night, because night would be all there is. Even in the twilight regions, the sun might sit forever near the horizon. This is more than a visual curiosity. It means time would be felt differently at the level of landscape. There would be no dawn chorus, no evening cooling, no long shadows arriving on schedule. A basic pulse we treat as universal would be missing. These worlds remind us that even something as ordinary as morning belongs to local physics. There are planets that orbit stars smaller and redder than ours. Most stars in the galaxy are not like the sun. They are smaller, cooler, and redder, belonging to a class called red dwarfs. That matters because many of the planets we find, especially small rocky ones, orbit stars like these. A planet around a red dwarf may circle very close in and still receive only modest warmth because the star itself is faint compared with the sun from the surface. If there is one to stand on, daylight might look coppery or dimmer than what we know. The star could loom larger in the sky because the orbit is tight, yet the light would feel different, filtered through a redder spectrum. These systems have become central to the search for habitable worlds because they are common and easier for astronomers to study. In a way, the future of planet hunting has shifted towards stars that once seemed unremarkable. Strange planets may be most abundant around the galaxy's smallest suns. Some worlds circle stars so active the skies may crackle constantly. A planet can be in the right place for liquid water and still be battered by the temperament of its star. This is a major concern around active red dwarfs, which can unleash fierce flares and bursts of charged particles far more often than the sun on the nearby planet. Such activity might hammer the atmosphere, flood the sky with radiation, and trigger dazzling but dangerous auroras that never feel rare. If the world has a magnetic field, the heavens could light up again and again in restless curtains. If it does not, the star may slowly erode the atmosphere itself that creates a powerful tension. In modern astronomy, some of the most promising planets for study orbit some of the most unruly stars. The result is a strange picture of possible habitability, one where a planet may sit in its star's tempered zone while living under a sky shaped by constant stellar anger, light, and electrical violence. Some planets may have been born far out, then migrated inward. A planet does not always stay where it forms. In many systems, giant worlds seem to have been born in the colder outer regions, where ice and gas were easier to gather, then slowly drifted inward through the disk that surrounded their young star. That journey changes everything around them. As a giant planet moves, it can scatter smaller worlds, steal material, or trap neighbors into precise orbital patterns. In some cases, it may plunge so close to the star that it becomes a hot Jupiter, a giant world now roasting in a place where it could never have formed in the first place. This idea transformed planetary science because it turned solar systems into restless places rather than neat diagrams. Worlds can travel. They can reshape the destinies of everything around them. A planet's present address may hide a long and turbulent past, written not only in what it is, but in where it ended up. Some planets may have moons, though we still have not confirmed one. For all the thousands of planets found beyond our solar system, not one moon has yet been confirmed beyond real doubt. That is astonishing when you think about how common moons are here. Jupiter and Saturn are surrounded by them. Even tiny worlds can have companions. It would be stranger if exoplanets had no moons at all. So astronomers keep searching for the faintest hints. Tiny changes in timing, delicate shifts in light, slight wobbles that suggest a moon is circling a distant planet we can barely detect. In the first place, the challenge is brutal because moons are smaller, dimmer, and easier to hide in the noise. Yet the search matters enormously. A moon can shape tides, stabilize a planet's tilt, and transform the possibilities for climate and life. Somewhere out there, alien moons almost certainly exist. We may be living in the brief era before the first one steps from theory into certainty. There are worlds packed more tightly than entire solar system neighborhoods. Some planetary systems make our own feel spacious. Astronomers have found stars surrounded by multiple planets, crowded into a region smaller than the orbit of Mercury. Picture several full worlds circling in the space we would normally assign to one the skies. If they had visible horizons, might be haunted by neighboring planets, looming much larger than Venus ever appears from Earth. In systems like these, gravity writes a more intricate score. Each planet feels the pull of the others. Their all bits settle into delicate patterns that can remain stable for ages, provided every world keeps perfect time. It is one of the most thrilling lessons from exoplanet discovery. Solar systems do not need broad spacing to survive. Nature can build them compact, intricate, and beautiful, like a clockwork city circling a single sun. The result is not chaos, but a kind of compressed elegance where many worlds live astonishingly close together, without immediately tearing one another apart. Some strange systems squeeze many planets closer than Mercury ever orbits. One of the clearest examples of planetary crowding is the TRAPPIST-1 system, where several Earth-sized worlds circle a tiny red star at distances that would all fit well inside Mercury's orbit. Yet because the star is so faint, those close paths do not automatically turn the planets into furnaces. Instead, it creates a strange inversion of what we expect. A region that would be impossibly hot around our sun can hold a whole family of worlds around a demo star. The planets pass one another at close range and tug on each other in rhythmic patterns locked into a chain of resonances that keeps their motion ordered. This gives the system an almost musical quality, as though each world is keeping time with the next. It is a reminder that the scale of a solar system depends on its star. A tiny sun can host a packed, intimate architecture that still leaves room for astonishing variety. A few planets may survive inside the swollen atmospheres of dying stars. When the sun-like star grows old, it swells into a red giant so enormous that nearby planets should be doomed. Yet some evidence suggests that certain worlds may briefly endure even as they plunge into the star's expanded outer layers. Survival in such a place would not mean calm orbiting beneath a peaceful sky. It would mean skimming through a vast stellar atmosphere, dragged by heat and friction perhaps, spiraling inward while disturbing the star from within. In some cases, a planet may be consumed. In others, it may help strip away stellar material or leave clues in the star's spin and brightness that betray its final struggle. This idea is gripping because it turns the death of a solar system into a contact event. A planet does not merely watch its star transform from afar. It can enter the star's out-of-body and interact with it directly. The last chapter of a world may unfold inside a sun. Some alien worlds may have seasons driven by wildly tilted orbits. On Earth, the seasons are shaped by the tilt of our axis, which gives us a reliable cycle of changing sunlight. But some planets may experience far more dramatic seasonal patterns if their axes are tipped at extreme angles. Imagine a world leaning so far over that one pole points almost straight at the star for part of the year, while the other sinks into long darkness. Such a planet would not have familiar spring, summer, autumn, and winter. It might swing between months of relentless heating and months of deep freeze, with strange transition periods in between the stars. Path across the sky would feel unnatural, perhaps circling the horizon or vanishing for ages. Climate on such a world could be difficult to predict, especially if oceans, clouds, or thick air redistributed heat in unusual ways. It reminds us that a season is not a universal experience. It is a local consequence of how a world chooses to lean. There are planets whose paths are so stretched their climates swing brutally. Not every planet travels on a near-circular path like Earth. Some follow highly elongated orbits that carry them close to their stars, then fling them far away. Again, that means a single year can include enormous swings in temperature and energy. A world might spend part of its orbit in comparative chill, then rushingward, and experience a surge of heating so extreme that its atmosphere expands. Chemistry shifts and any stable weather pattern is thrown into ground confusion. This is not simply a longer winter and summer. It is a planet moving between two very different physical states as it loops around its star. The changing distance affects light, heat, and even winds in ways that would make Earth feel almost impossibly calm. By comparison, such worlds are thrilling because they show that a year can be a drama, not a cycle. Orbit itself can become the engine of planetary violence, rewriting the climate again and again. Some giant worlds may be heated more by types than starlight. The planet does not need to hug its star to become hot. In some cases, gravity from a star, a nearby planet, or a moon can flex a world so relentlessly that the interior heats from within. This is called tidal heating, and in extreme cases, it may rival or exceed the warmth the planet gets from starlight. We see a modest version of it in Jupiter's moon Io, but exoplanets could take the idea much further. If a giant world follows an eccentric orbit, its shape may be stretched and relaxed over and over again, kneading the interior with every pass. That friction can generate immense heat-drive internal motion and possibly transform the atmosphere and surface. It is a thrilling reversal of instinct. A planet can glow with energy, not because the star is close, but because gravity is constantly working it like a living machine. A world can be cooked by motion itself. A few planets may glow red from constant volcanic resurfacing. There may be worlds where volcanoes are not occasional disasters, but a permanent part of the landscape. On such planets, tidal heating, youth, or internal chemistry could keep magma rising, so often that the surface is continually renewed. Fresh lava would darken, crack, and cool, only to be broken open again by newer flows from a distance. Parts of the planet might glow with a dull red heat, especially on the side facing away from direct starlight. This is more than a dramatic image. Constant resurfacing changes the whole character of a world. It can refill the atmosphere with gases, erase impact craters, and keep the crust from growing old. A climate like that would not feel settled. It would feel restless and unfinished, as if geology had been turned up too high. We are used to imagining planets as ancient and stable. Some may instead be places where the ground itself is always in the process of becoming new. Some rocky worlds may have crusts made from minerals rare on Earth. Earth's crust feels ordinary only because it is home. In truth, the minerals that dominate our planet reflect a very specific history of temperature, chemistry, water, and plate activity. Change those ingredients and an entirely different kind of rocky world may emerge. Some exoplanets could have crusts rich in minerals that are rare at Earth, surface shaped by hotter conditions, unusual elemental ratios, or the absence of water-based weathering. On a carbon-rich world, for example, the upper layers might include forms of carbon, bearing rock far more abundant than anything common here. On an ultra-hot rocky planet, the surface could be built from minerals stable only under brutal heat with familiar Earth rocks, unable to survive for long. This matters because the crust is not just scenery. It controls how a planet reflects light, releases gases, stores heat, and changes over time. Even stone itself may tell very different stories. On strange planets, there are planets where noon may be hot enough to melt stone. On some rocky exoplanets, the star beats down with such force, that midday temperatures may rise high enough to melt the ground itself. This is not the warmth of the desert or the heat of a volcano. It is a planetary noon so intense that rock can soften glow and perhaps even flow across the surface in molten patches. On worlds orbiting red dwarfs at very close range, or on ultra-short period planets whipping around their stars in only hours, the dayside can become a place where ordinary geology stops behaving in deeply ordinary ways. Mountains may slump, minerals may vaporize, the boundary between surface and atmosphere may begin to blur. What makes this so striking is how it changes the meaning of daylight we think of, known as the bright center of the day. On these planets, it becomes a destructive force. Sunshine is no longer life-giving or pleasant. It is a furnace descending from the sky. Some strange worlds may have nights brightened by rivers of lava. Darkness on another world does not always mean blackness. On a planet with active volcanism or molten regions, the night side may be lit by lava flows, glowing cracks, or heat radiating from recently erupted rock. Imagine standing beneath the sky of stars while the land around you shines red in branching lines as though the planet were lit from below by its own wounds. This is one of the most haunting possibilities in exoplanet science because it gives night a different source of light. No moon is needed. No sunrise is coming. The brightness belongs to the world itself. On a tidally locked planet with a searing dayside, some of that heat may even be carried toward the darker hemisphere, feeding volcanic regions or magma movement beyond the line of eternal sunset. A world like this would feel alive in an unsettling way, glowing not with reflected light, but with exposed fire from within. A few planets may hide deep oceans beneath global shells of ice. Some distant worlds may look frozen and lifeless from the outside, while hiding something extraordinary below. If a planet or large moon has enough internal heat, perhaps from radioactivity or tidal flexing, a thick shell of surface ice could cover a deep liquid ocean beneath. That means an apparently silent white world might contain a vast dark sea sealed away from space for ages. The ice above would not be a mere crust, but a roof over an alien ocean, protecting it from radiation and preserving heat below. In our own solar system, moons like Europa and Enceladus make this idea feel real and urgent. Beyond the solar system, similar worlds may be common. The fascination here is profound. A planet can conceal its most interesting feature under miles of ice. A frozen face does not always mean a frozen heart. Sometimes the most promising ocean on the world is the one no telescope can directly see. Some ocean worlds may never have a single continent anywhere. Earth's oceans are vast, yet they are broken by continents that shape climate currents and the history of life. Some exoplanets may never have any land at all. Their surfaces could be one continuous global sea, uninterrupted by coasts, mountain ranges, or river-carved boundaries. From space, such a planet might look almost serene, a round blue world with clouds drifting above an unbroken ocean. But the absence of continents would change everything. Weather patterns might be more uniform in some ways and more extreme in others. Nutrient cycles would be different. There would be no beaches, no soil, no rocky shore where land and sea meet. Even the chemistry of the atmosphere could follow a different path over time. What grips the imagination here is how thoroughly this alters the meaning of a planet. We often think of land as normal, yet a world can exist with no dry place at all, only water from horizon to horizon. There are planets that may be richer in carbon than Earth. Earth is not the only recipe for a rocky world. If a planet forms in a region where carbon is especially abundant compared with oxygen, then resulting world may be built from a very different chemical foundation. Instead of the silicate-heavy geology that dominates Earth, such a planet might contain far more carbon-based materials woven through its crust and mantle. This could change everything from the minerals of the surface to the way heat moves through the interior. A carbon-rich planet would not necessarily be a glittering fantasy of diamonds everywhere. It might be dark, dense, and geologically unfamiliar, filled with substances that are unusual here, but natural there. The thrill of these possible worlds lies in what they reveal about planetary diversity. A rocky planet does not have to mean Earth like nature can take the same broad idea, a solid world, under gravity, and build it from an entirely different chemical imagination. Some carbon-rich worlds may form layers of graphite or diamond. Under the right conditions, a carbon-rich planet may do something almost unbelievable. Deep inside immense pressure, could squeeze carbon into crystal structures, such as diamond, while shallower layers might contain graphite or other carbon-heavy materials. This does not mean a sparkling jewel world waiting to be mined. It means a planet whose interior geology could be shaped by the same element that forms both soot and gemstones. On Earth, but on a scale that defies ordinary thought. The deeper one goes, the more pressure transforms simple chemistry into something harder and stranger. That possibility matters because it shows how planetary interiors depend on composition as much as size. A world made from a different elemental starting point may not just look different on the surface, it may be fundamentally different all the way down. Beneath an alien crust, entire layers of carbon could be stacked like an unfamiliar geological poem, written under crushing force and time. A few strange planets may have atmospheres stripped by fierce stellar wind. A star does more than shine. It also blows a stream of charged particles outward, and on some planets that wind may be fierce enough to erode the atmosphere itself. Worlds orbiting close to active stars are especially vulnerable. Over long spans of time, the upper air can be heated, ionized, and gradually carried off into space. This process can transform a planet's fate. A world that once had a thick envelope of gas may be left bare, dry, and far more exposed than before. The violence is slow on the human timescale, but it is relentless. It turns habitability into a race between atmospheric replenishment and stellar attack. For astronomers, these stripped atmospheres are not just losses, they are clues. By watching gas escape, scientists can infer the strength of stellar winds and the fragility of planetary air. A planet's sky is not always stable. Sometimes it is something the star is actively trying to steal. Some small worlds may be little more than exposed planetary cause. Among the strangest exoplanets are small, dense worlds that may once have been much larger. Astronomers think some of them began as sub-Neptunes or gas-rich planets wrapped in thick atmospheres. Then over time, intense radiation and stellar wind blasted those outer layers away, leaving behind a hard central Roman. What remains may be an exposed planetary core, the stripped heart of a world that lost almost everything around it. This is fascinating because it turns planets into archaeological objects. A dense rocky body may not be a planet that was born small. It may be the survivor of a long process of planetary erosion. In a sense, we are looking at the skeleton rather than the body. These worlds show that planets are not fixed categories. A gas-rich world can become something leaner, harsher, and more compact. Sometimes the most revealing part of a planet is the part left behind after its outer self is gone. There are planets that seem to have lost almost everything but their center. Some exoplanets feel less like complete worlds and more like remnants. They are extremely dense, very close to their stars, and so stripped down. The astronomers suspect they may be the surviving centers of much larger planets. Imagine a world once wrapped in deep gas or volatile rich layers orbiting too near a star that gradually cooked and blew those outer regions into space. What remains could be the core compressed, battered, and left exposed after billions of years of loss. This idea is powerful because it gives planets a biography of attrition. We are not only seeing how a world forms, but how it can be peeled back until the innermost part is all that is left. It also changes how we look at small rocky planets near hot stars. Some may not be pristine little Earths, they may be the leftover hearts of giant worlds surviving after nearly everything else was erased. Some giant planets may orbit sideways over their stars' poles. We tend to imagine planets circling above the star's equator because that is how our solar system is arranged. Yet some giant exoplanets break that rule spectacularly. Their orbits are steeply tilted, and a few may pass almost over the stars, poles moving in paths that would look sideways compared with the neat flat layout. We know this is one of the clearest signs that solar systems can experience major upheaval. Such orbits may be the result of violent interactions with other planets or nearby stars, events that knocked a giant world out of its original plane and left it circling at an astonishing angle. The result feels deeply strange because it turns a solar system from a calm disk into a three-dimensional puzzle. A planet can rise over a star's pole rather than slide around its waist. Even orbital direction, something that once seemed fundamental, turns out to be another place where nature likes to improvise. A few strange worlds move on paths badly misaligned with their stars. Our solar system taught us to expect order. The planets circle in nearly the same flat plane like marbles, rolling around a well-made track. But some exoplanets ignore that pattern completely. Their orbits are badly tilted compared with the spin of their stars, as if the whole system was knocked sideways long after it formed. This is one of the clearest signs that planetary systems can suffer violent pasts. A giant world may have been shoved by another planet, tugged by a distant star, or dragged into a new angle through a long gravitational struggle. The result is a path that cuts across the star's equator at a bizarre slot. From afar, that may seem like a subtle detail. It is anything. But it tells us that some worlds are not living in calm architecture. They are survivors of upheaval, still carrying the crooked signature of old cosmic collisions in the shape of their ears. Some planets may have been flung into lonely space by gravitational chaos. A planetary system can look stable for millions of years, then suddenly turn brutal. When several giant worlds form together, their gravity can begin a slow contest of nudges and near misses. One orbit shifts then another, a resonance breaks, a close encounter happens, and in that moment, a planet may be hurled outward with such force that it escapes the star entirely. What was once a member of a solar family becomes a castaway. This kind of ejection may be one of the main ways rogue planets are made. It turns planetary history into something dramatic and precarious. A world can begin in a bright young system full of heat dust and neighboring planets, then end up drifting through interstellar darkness because gravity became unstable for just long enough. That possibility makes every quiet orbit feel less guaranteed. A planet is not always born to stay. Sometimes it is born into a family that eventually throws it away. There are rogue worlds warmed only by radioactivity and trapped heat. A planet without a star sounds like a frozen corpse. Yet some rogue worlds may keep a fate in a warmth for billions of years, even while drifting through the dark between stars. The source would not be sunlight, but the slow decay of radioactive elements in the interior, combined with the leftover heat from the planet's own formation deep below the surface. That heat could linger like an ember sealed inside stone. If the planet were large enough and wrapped in insulating layers of rock or ice, the temperature underground might remain surprisingly stable. What groups the imagination is how little a world may need to avoid becoming completely dead. No dawn, no seasons, no star overhead, and still somewhere beneath miles of darkness heat might endure. It is a powerful correction to our instincts. A planet does not need to live beside a sun to keep a hidden source of energy. Sometimes the fire is carried within. Some free-floating planets may still carry thick blankets of atmosphere. When a planet is flung into interstellar space, it does not automatically lose everything that made it a world. Some may keep dense atmospheres long after leaving the star that once warmed them. That matters because a thick atmosphere can act like a blanket trapping internal heat and slowing the loss of warmth into space. Hydrogen is especially good at this, and on a large enough rogue planet, it could help create a surprisingly insulated environment from the outside. Such a world would look cold and dark, but the atmosphere could be doing quiet work holding on to what little energy remains. This idea changes the emotional texture of a rogue planet. It is no longer just a lonely rock in the void. It may be a sealed world wrapped in its own sky, carrying a remnant of habitability into the black. A planet cast out by gravity may still remain self-contained, secretive, and strangely alive with retained warmth. A few lonely planets may even keep dark, hidden liquid water. The phrase liquid water usually brings sunlight to mind, beaches, rivers, or at least a warm star in the sky. But a rogue planet may not need any of that if the conditions are right. Beneath a thick atmosphere or under a crust of insulating ice, internal heat could be enough to keep water in liquid form far below the surface. That means one of the most important ingredients for life might exist on a world where no sunrise has happened for billions of years. The water would not glitter. It would not lie beneath clouds lit by a sun. It would remain in darkness, hidden and sealed away. That possibility is astonishing because it widens the map of where life-friendly conditions might exist. Habitability becomes less about location and more about structure. A planet can leave its star behind and still protect an inner sea. The galaxy may contain warm, wet worlds drifting through absolute night. Some strange worlds may be born in disks twisted by companion stars. Planetary systems do not always form around a single star shining alone. Many stars are born with companions, and those companions can twist the surrounding disk of gas and dust into strange shapes before any planet has fully emerged. Instead of a flat, orderly pancake, the material may become warped, tilted, or even broken into separate rings that do not line up. Planets forming in such an environment would grow inside a birthplace already bent out of shape. Their orbits could end up unusual from the very beginning, not because of later chaos, but because the nursery itself was distorted. This matters because it gives us another route to planetary weirdness. A strange orbit does not always mean a violent past. Sometimes it means a strange childhood. The presence of another star can reshape the cradle before the worlds inside it are even finished. Nature may be building odd planets from crooked blueprints right from the start. There are planets and systems where two suns chase each other endlessly. In a binary star system, the two suns do not sit still while the planet calmly circles them. They chase each other, each pulled by the other's gravity, moving around a shared center in a ceaseless loop. A planet in such a system must live with two moving sources of light, each shifting position as the days and years pass. The sky would never feel simple. Sometimes the stars might appear close together, and other times they would separate. One might set while the other still burns above the horizon. The beauty of this arrangement is matched by its difficulty. Planetary orbits in such systems must find a stable rhythm among constantly changing gravitational forces. Yet some do. That is what makes them so captivating. They prove that even a sky ruled by two suns in motion can still host a lasting world. A system that seems too complicated for stability can become a home for planets. After all, some double sun worlds may see shadows crossing in complicated rhythms. On Earth, shadow is simple. One sun means one dominant direction of light. On a planet orbiting two stars, light becomes more theatrical. If the suns are separated enough in the sky, objects could cast two shadows at once each, pointing a little differently, each changing as the stars move. One shadow may sharpen while the other fades. At certain moments, they could overlap. At others, they might stretch apart across the ground like crossed fingers. Even a simple day would feel more layered. Morning and evening would not arrive in one clean sweep because the stars might rise and set at different times. Imagine landscapes where the light never settles into a single mood because the sky itself is working in pairs. This is not merely pretty. It reveals how profoundly a star system shapes the experience of a world. A second sun does not just add brightness. It adds complexity to every hour, every outline, and every moving shape. A few planets orbit stars that pulse, flare, or fade dramatically. Not every star is steady. Some brighten and dim in regular cycles. Some erupt with sudden flares. Others pulse as their outer layers swell and shrink. A planet circling such a star would live under a sky where the source of light itself behaves unpredictably or rhythmically in ways that would reshape weather, temperature, and atmosphere. Imagine a world where daylight strengthens and weakens, not because of clouds or seasons, but because the star itself is changing. In a flare-rich system, the sky may suddenly flood with radiation in a pulsating one. The planet could experience recurring shifts in energy, as though the sun were breathing. These stars remind us that planets do not orbit passive lamps. They orbit active bodies with personalities of their own. A strange planet may be made strangers still by the star. It depends on. Sometimes the weirdest thing in the system is not the world, but the sun above it. Some worlds circle pulsars, the spinning corpses of exploded stars. A pulsar is what remains after a massive star explodes, and its core collapses into an object so dense and fast spinning that it sweeps beams of radiation through space like a cosmic lighthouse. The first confirmed exoplanets were found around one of these stellar remnants, which still feels astonishing. Planets around pulsars do not orbit warm sunlight, they orbit the aftermath of catastrophe. The star they knew, if they knew one at all, is gone. In its place is a tiny savage remnant spinning with terrifying speed. That such planets exist at all was a shock, because a supernova seems like the sort of event that should erase any nearby world. Yet there they are circling the corpse of an exploded star. It is one of the strangest beginnings in exoplanet science, and it permanently widened the imagination. The planet can exist not only around the sun, but around the fierce compact remnant left after that sun died violently. There are planets that may have survived a supernova long ago. When a massive star explodes as a supernova, the event releases staggering energy, hurls material into space, and transforms the system. In an instant, it feels like the end of everything nearby. Yet some planets may survive such an event, especially if they orbit far enough away, or if their paths and timing unfortunate. Survival would not mean staying unchanged. The blast could strip atmospheres, alter orbits, and leave the world in a system now ruled by a neutron star or black hole. Even so, the planet endures. That is what makes the idea so compelling. A world cannot live its own sun's violent death. In a sense, it becomes a witness to cosmic disaster, still circling after the light source that once shaped its climate and sky has vanished forever. Survival on that scale feels almost mythic. A planet may carry on through an explosion that briefly outshines an entire galaxy and continue its silent orbit afterward. Some giant worlds may be slowly spiraling toward destruction. Not every orbit lasts forever. Some close and giant planets are losing energy through tidal interactions with their stars, which means their paths may gradually shrink over immense spans of time. The process is slow beyond human comprehension, but the destination is clear. Sooner or later, the planet may fall inward far enough to be torn apart, evaporated, or swallowed. This gives certain worlds a tragic quality. They are not merely hot Jupiter circling too close. They may be doomed giants each year, bringing them imperceptibly nearer to the end. The star raises tides in the planet raises tides in the star, and in that exchange, a little orbital energy is lost. Over millions or billions of years, it adds up. Astronomy often deals in things that feel timeless. These worlds remind us that even an orbit can have a death sentence. A giant planet may spend ages circling its star while very slowly falling toward annihilation. A few planets are close enough to be stretched by tidal force. Gravity does not pull equally on every part of a nearby world. If a planet orbits very close to its star, the side facing inward feels a stronger pull than the far side. That difference creates tidal force, and if it is strong enough, it can literally stretch the planet. The world may become slightly elongated rather than perfectly round, with its shape pulled into something more oval by the star's constant grip. This may sound like a minor distortion, but it changes the inner life of the planet. Tidal stress can flex the interior, generate heat, and help drive geological activity. It can also lock the rotation and influence the atmosphere. What is thrilling here is how physical the relationship becomes. The close planet is not merely warmed by its star. It is handled by it, pulled into shape by a force that never fully lets go. Even the body of a world can be molded by proximity. Some alien worlds may be literally falling apart under their star's pull. There comes a point where tidal force stops being a sculptor and becomes an executioner. If a planet moves too close to its star, gravity can begin stripping material away from it, especially if the world is already fragile or loosely held together. Rock, gas, or dust may stream outward, forming tailings that betray the destruction. In some cases, astronomers have found evidence for disintegrating worlds that seem to be shedding material orbit after orbit. It is one of the most dramatic fates a planet can suffer. Rather than exploding in a single instant, it comes apart piece by piece, slowly unmade by the same gravity that once kept it in motion. The image is unforgettable. A planet does not always die with impact or fire. Sometimes it dies by erosion on a cosmic scale, crumbling under relentless pull. A world can be transformed from a solid place into a drifting trail of debris, still circling as it vanishes. There are planets whose upper skies leak heavy elements into space. We often imagine the gases escaping from a planet as the lightest ones, especially hydrogen and helium. Yet on the hottest worlds, astronomers have detected signs that heavier elements may also be present, high in the atmosphere and perhaps escaping into space. This is extraordinary because it means the upper layers can be heated and stirred so violently that metals and other heavy ingredients are carried upward into regions where they can be stripped away. In such a sky, the distinction between air and loss begins to blur. The atmosphere is not merely sitting above the planet, it is being lifted, sifted, and peeled back under intense radiation. This gives certain exoplanets a raw, exposed quality, as though the star is not only shining on them, but actively pulling at their chemistry. A planet can reveal what it is made of by losing pieces of itself. Even heavy elements may end up joining the long escape into space. Some strange atmospheres contain water vapor, carbon dioxide, or metal traces. One of the great triumphs of modern astronomy is that we can begin to read the chemistry of worlds we cannot directly visit. As an exoplanet passes in front of its star, a small fraction of starlight filters through the atmosphere, and different molecules leave different marks in that light. That is how astronomers have found signs of water vapor, carbon dioxide, sodium, potassium, and even hints of metal-bearing gases in distant skies. It is a remarkable achievement. When you stop and think about it, we are not just finding planets anymore. We are sampling their air from across light years. Each detection changes a world from a dot into a place with weather, chemistry, and physical character. Some atmospheres look hazy, some appear enriched in specific elements, some remain frustratingly hard to decode. But the larger revelation is already profound. A distant planet's sky is no longer unknowable. It can leave a chemical signature in light. A few planets show chemistry that changes from morning side to evening. On a tidally locked world, the side turning into day and the side turning into night may not share the same atmospheric chemistry. As gas circulates around the planet, molecules can form, break apart, condense, or reappear depending on local temperature. That means the atmosphere on the morning side, where gases are emerging from cooler darkness, may differ from the evening side, where they have just endured intense heating. This is one of the strangest refinements of exoplanet science. We are no longer just asking what chemicals a planet has. We are asking how those chemicals vary around the globe. A world can have different atmospheric personalities depending on which limb you observe. Effect turns a planet into something more dynamic than a single average description. It has regions, transitions, and moving zones of chemical change. Even the sky can have a daily geography with sunrise and sunset leaving different fingerprints on the air. Some worlds may have gigantic cyclones locked in place for years. The planet does not need continents to build a massive storm. In fact, some of the biggest and longest-lived storms may arise on worlds with deep, uninterrupted atmospheres where energy can flow for years without meeting land. Giant exoplanets may host cyclones so vast they dwarf Earth, and some could remain in roughly the same place for long periods. If winds, rotation, and heating all line up just right, we already know of giant persistent storms in our own solar system, So on hotter, faster, or more turbulent worlds, the possibilities become even more dramatic. Imagine a storm large enough to swallow our planet many times over, spinning beneath clouds that never clear. A feature like that would not be weather in the everyday sense. It would be part of the planet's identity. When astronomers infer large-scale atmospheric patterns on distant giants, they are glimpsing worlds where storms may become semi-permanent, landmarks in an endless moving sky. There are planets whose cloud decks may sit above infernal heat. From a distance, a cloud-covered planet can look almost calming. Clouds soften the world, they hide the harshness below. Yet some exoplanets may wear that softness as a mask. High in the atmosphere, clouds of exotic material could drift in relatively cooler layers, while far beneath them the temperatures climb into truly brutal territory. The visible cloud deck becomes a kind of full surface concealing a deep furnace below. This contrast is part of what makes giant planets so hypnotic. What looks serene from above may be sitting over pressures and heat that defy imagination. On a hot giant, clouds might form from silicates, metals, or condensed minerals floating far above layers. Where the atmosphere grows dense, compressed, and savage, the world can appear wrapped in pale brightness while hiding conditions closer to an industrial blast furnace. The beauty is real, but it is only skin. Deep below the clouds, the planet may be all violence. Some giant worlds may have hazes that hide everything below. Astronomers often won't appear deep into an exoplanet's atmosphere, but some worlds refuse to cooperate. They are cloaked in high hazes made of tiny particles that scatter light so effectively that they block the view of the layers beneath. This can turn a promising target into a mystery. The planet is there, the atmosphere is there, but the details are hidden behind the veil. These hazes may be produced by complex chemistry, driven by ultraviolet light, or by the condensation of exotic materials, high above the deeper weather systems. The result is a world whose visible character is dominated not by what lies below, but by a suspended curtain in the upper air. It is a beautiful frustration. A giant planet can keep its secret simply by growing a thick enough haze. Even with advanced telescopes, some worlds remain silhouettes with atmospheres we can only partly read, like faces seen through frosted glass. A few strange planets may smell of sulfur metal or burnt rock. No one has stood on an exoplanet and taken a breath, but chemistry lets us imagine the scent some of these worlds might carry. On a hot, rocky planet with volcanic gases rising into the air, sulfur compounds could dominate, giving the atmosphere the sharp sting of matches or rotten eggs. On a scorched giant with vaporized metals high in the sky, the air might carry something harsher, more like a furnace or hot machinery. On worlds where silicates and mineral gases are lifted from molten surfaces, the smell could resemble stone dust, ash, or rock pulled fresh from a kiln. Of course, many of these atmospheres would be lethal long before scent mattered. That is part of what makes the idea so gripping. Smell is intimate. It makes a distant world feel suddenly physical. The universe is not only full of strange places to see, it may be full of strange air with strange chemical signatures waiting in the dark. Some worlds likely have weather patterns no Earth language can describe. Earth gave us rain, snow, hail, wind, fog, and storm, but those words belong to one planet, with one set of materials and one narrow range of conditions. Elsewhere, weather may operate on combinations that our language was never built to hold. A world with mineral clouds, metal vapor, supersonic winds, and permanent day on one side may not experience anything we would comfortably call the storm. A gas giant with deep layers of chemistry crushing pressure and heat rising from within may host motions that blur the line between weather and internal circulation. Even our most familiar terms begin to fail. We can describe components, but not always the lived character of the whole. That is one of the most beautiful consequences of exoplanet science. It reveals how parochial everyday language really is. Somewhere in the galaxy, the sky is doing something real, complex and majestic and human. Speech does not yet have a simple name for it. There are planets with densities lighter than cork and almost as strange. Some planets are so low in density, they seem to belong more to imagination than to astronomy. These worlds can be as wide as giant planets, yet so light for their size that cork becomes a useful comparison. The image is unforgettable. A planet broader than Jupiter, yet fluffier than something you could hold between your fingers. Of course, no literal cork planet exists. These are vast worlds of gas, with atmospheres so inflated and extended that the total density becomes astonishingly small. Their weak out of gravity lets the atmosphere puff outward, making the planet look oversized and almost fragile. What makes them especially strange is that they do not fit neatly into familiar categories. They are not small rocky worlds. They are not compact gas giants. They sit in the weird middle ground where planetary bulk becomes deceptive. The silhouette is enormous. The substance is almost airy. They look like giants, yet, in some deep physical sense, they are barely holding together. Some super-puff planets may hold huge atmospheres around tiny cores. A super-puff planet may be one of the most misleading objects in astronomy. From its size alone, you might expect a massive world with crushing gravity and a thick, deep interior. Instead, some seem to be built around surprisingly small cores, wrapped in vast shells of gas. The atmosphere does most of the visual work. It expands outward, making the planet appear grand and swollen, while the hidden center may be only a modest fraction of the total size. That structure is fascinating because it hints at delicate timing in planetary history. The core had to gather enough gas before the disk around the star disappeared, yet not so much that it became an ordinary giant. Something unusual happened, and the result is a world that feels exaggerated all out of presence and relatively little in a bulk. It is a reminder that planets are not judged well by outline alone. A huge planetary radius can conceal something surprisingly slight beneath the clouds. A few planets seem too large for their mass and age. Astronomers sometimes find worlds that appear to be an open defiance of expectation. Their measured size is too big for the amount of mass they contain, or too large for how old they seem to be. According to standard models, such planets should have cooled and shrunk more by now, yet they are still inflated, still oversized, as if some hidden process were propping them up from within. This puzzle is one of the great pleasures of exoplanet science. Means the universe is still withholding part of the answer. Maybe intense stellar radiation is heating the atmosphere more efficiently than expected. Maybe internal energy is being transported in a strange way. Maybe tidal effects are helping. Whatever the cause, these planets feel unfinished, like worlds refusing to settle into their predicted final form. They remind us that a planet is not just a lump of matter in orbit. It is a thermal story. And some of those stories are still resisting explanation. Some young worlds may still be glowing from the violence of formation. Planets do not arrive quietly in their youth. They are shaped by collisions, falling gas, and the relentless compression of gravity. All of that leaves heat behind. A young world may shine in the infrared because its formation was so energetic that it is still cooling from the process. That means astronomers can sometimes detect a planet not because it reflects its star, but because it retains its own fresh wolf. It is an astonishing thought. A planet can still be hot from being born. The violence here is not metaphorical materials slammed together, gravity-squeezed inward gas, crashed onto a growing world and released energy in the process. When we see a young glowing planet, we are witnessing a body that has not yet forgotten those events. It still carries them in its temperature. These worlds make planet formation feel immediate rather than ancient. They are not fully settled objects. They are warm survivors of a recent and turbulent beginning. There are planets we can photograph directly glowing beside their stars. Most exoplanets are found indirectly through dinning wobbling or some other subtle effect. That is why direct images feel so extraordinary. In a few rare cases, astronomers have managed to block out the starlight and capture actual pictures of giant planets glowing beside their stars. The planets in these images are usually young, massive, and far from their suns, which makes them easier to separate from the overwhelming glare. Even then, the technical challenge is immense. A star is so bright that seeing a nearby planet is like trying to notice a firefly beside a floodlight from across a continent. Yet we have done it, and what we see are not crisp little spheres with surface detail, but real planetary points of light hanging in. Darkness around another sun that changes something emotional in the mind. A planet stops being an inferred statistic and becomes visible, present, and undeniably there. One glowing world among the stars. Some strange worlds are so young, they still radiate their birth heat. There are exoplanets so young that they have barely entered planetary maturity. They are still contracting, still cooling, and still shedding the heat stored during their formation. In practical terms, this means they can shine more brightly in infrared light than older planets of similar size. In human terms, it means there are newborn worlds still warm from the nursery. That youth matters because it gives astronomers a rare chance to study early planetary evolution while it is still happening. The atmosphere may still be settling, clouds may be forming and changing the planet's internal structure may not yet have reached the quiet balance it will hold later. These are not just planets at a younger age. Our planets in a more revealing state when the signatures of their origins have not yet faded. A mature planet hides much of its childhood. A young glowing one still carries it openly, radiating the heat of its recent arrival. A few giant planets orbit incredibly far from their parent stars. Some giant exoplanets circle of distances so vast that they feel almost detached from the stars they belong to. Instead of hugging close like hot Jupiters, they wander on wide orbits that can place them many times farther out than Neptune's from the sun at subdistances. The star would shine weakly more like an intensely bright star than a dominating sun. Any moons around such a planet would live in a dim outer kingdom where planetary light and internal heat might matter almost as much as starlight. These far-flung giants are fascinating because they stretch the usual picture of planet formation. Building a massive planet so far out should be difficult. Material is sparse, growth is slow, and yet nature has clearly done it, or something close to it. In at least some systems, these worlds feel like outposts, giant presences circling at the edge of their systems, where the parent star begins to lose its authority. Some far-flung worlds challenge how planets are supposed to form. Classical formation models work best when giant planets arise in the colder outer regions of a disk, but only within a certain range where enough material is available quickly enough. Push that distance too far, and the process becomes difficult. That is why some wide orbit planets are so provocative. They seem to exist in places where standard core growth should struggle badly. This opens the door to deeper questions. Did they really form where we see them now, perhaps through a different process more like the birth of a small star? Or did they form closer in, then get scattered outward through gravitational encounters? Either answer is thrilling, because either one means the system has a more dramatic history than a simple calm disk would suggest. These worlds matter not just because they are distant, but because they expose the limits of our neat explanations. They sit out there like stubborn clues, forcing theory to follow where observation has already gone. There are planets discovered not by light, but by gravity's fingerprint. Sometimes a planet is found without ever dimming its style, being directly imaged. Instead, its existence is revealed by what gravity does to light or motion around it. One powerful example is gravitational microlensing. If a star passes in front of a more distant background star, its gravity bends and magnifies the background light. Add a planet to the foreground star, and the magnification pattern changes in a telltale way. For a brief moment, gravity itself becomes the detector. This is a wonderful kind of discovery because it feels so indirect and yet so precise. A world announces itself not by shining, but by warping the geometry of the light behind it. Many of the planets found this way are distant, hard to revisit, and unlike the close-in systems most other methods favor. So microlensing expands the map. It reveals worlds through the shape of gravity, as though the planet left its signature on a beam of light passing far away. Some worlds reveal themselves only when they briefly dim their star. One of the most productive ways to find exoplanets is also one of the most elegant. If a planet crosses in front of its star from our point of view, the starlight dips by a tiny amount. That brief dimming can reveal the planet's size, its orbital period, and sometimes much more. It is a delicate method that depends on perfect alignment, which means most planets never show themselves this way. But when one does, the effect is profound. A world invisible in every direct sense suddenly becomes detectable because it casts the smallest possible shadow across its sun. That shadow can repeat like clockwork, turning a faint blink in starlight into the proof of an orbiting planet. There is something deeply moving about that we discover a world because for a moment it interrupts the light. A distant planet becomes known not through brightness, but through a tiny rhythmic act of eclipse. A few planets were found because they made their stars wobble. A star does not sit still while a planet orbits it. Both objects move around a shared center of gravity, though the star's motion is much smaller. Astronomers can detect that motion as a subtle wobble revealed by tiny shifts in the star's light as it moves toward us and away again. This radial velocity method was one of the first great pathways into exoplanet discovery, and it remains one of the most important. It gives us not only the presence of a planet, but also a clue to its mass. The beauty of this method lies in how intimate the physics is. A planet too faint to see still makes its star sway. It leaves a pool in the starlight. That means a world can be found through influence alone. No shadow, no image, just a repeating signature in the movement of the distant sun. The star tells on the planet by dancing, and astronomers have learned how to read the steps. Some alien worlds are known mainly from the heat they give off. Not all planets are found through starlight. Some are studied chiefly through their own thermal glow, especially young and giant worlds whose internal heat still leaks outward in infrared light. This allows astronomers to learn about atmosphere's cloud structure and temperature without relying entirely on reflected light from the parent star. In a sense, the planet is introducing itself through warmth. That is a very different kind of discovery from a transit or wobble. It feels more like catching the body heat of a world in the dark. These planets are especially important because they can be observed in ways that more mature or smaller worlds cannot. The heat becomes a source of information, revealing whether the atmosphere is cloudy, whether chemistry varies, and how the world is cooling with time. A planet does not always need to block light or pull visibly on a star. Sometimes it is known because it is still quietly glowing on its own. There are planets we infer from dust gas and broken orbital pattern. Sometimes astronomers do not find a planet directly at all. Instead, they see signs that something planetary must be there. A disk of dust may contain a sharp gap, as though an unseen world has cleared a lane through the material. A ring may be warped or asymmetrical. Gas may flow in patterns that suggest a hidden gravitational sculpture. In mature systems, the orbit of one known planet may be slightly off, hinting that another unseen companion is tugging on it. This is one of the most detective-like parts of astronomy. A planet leaves tracks without showing its face. It changes the environment around it, and from those changes, astronomers work backward toward the unseen world responsible. It is a reminder that planets are agents as much as objects. They carve, pull, disturb, and organize. Even when we cannot yet point to the planet itself, we may already be reading the evidence of its presence written into dust, gas, and orbital behavior. Some systems may still be building strange planets right now. Planet formation is not only a story of the distant past. In some young systems, it may still be happening right now around newborn stars. Disks of gas and dust can show rings, spirals, gaps, and clumps that look like the fingerprints of worlds in the process of growing. Somewhere inside those disks, material may be piling onto planetary cores. Atmospheres may be gathering, and migrating worlds may already be reshaping the structure of the whole system. This is thrilling because it turns a theory of origins into an observable event. We are no longer limited to guessing how planets once formed. In some cases, we may be watching the architecture emerge while the builders are still at work. The systems are messy, luminous, and unresolved, which makes them feel alive with possibility. A strange planet does not need to be fully finished matter. Sometimes the most fascinating world is the one still hidden in dust on its way to becoming. A few worlds may be trapped in resonant dances with neighboring planets. Some planetary systems achieve a kind of gravitational choreography so exact that neighboring worlds fall into resonance. One planet may orbit twice for every 3 orbits of another, or follow some other repeating ratio that keeps their pools organized rather than chaotic. This matters because resonance is not just a mathematical curiosity, it reveals history. Planets often enter these patterns while migrating through the disk, early in a system's life, becoming locked together as they move. Once established, the resonance can preserve stability and create an elegant chain of repeated motion from the surface. Of such a planet, if anyone could watch the neighboring worlds over long periods, their appearances would recur with uncanny regularity. It would feel as though the whole system were keeping time. What makes this beautiful is that gravity alone creates the pattern, no hand arranges it. The planets themselves fall into rhythm, and the solar system begins to behave less like a crowd and more like music. Some planets tug one another so precisely they run like clocks in tightly packed systems. Planets can interact so regularly that their motions become exquisitely predictable. Each world pulls on the others at just the right moments, causing slight variations in orbit that repeat with stunning precision. These systems are not perfectly simple, yet they can behave like elaborate clocks with every planet helping set the pace of the rest. Astronomers love this because such patterns let them measure masses, infer hidden companions, and test whether the whole architecture is truly stable. But beyond the science, there is something almost poetic about it. Multiple worlds, each with its own ear, each shaped by the gravity of the others, all maintaining a shared order over immense spans of time. It is a form of cosmic cooperation without intention. The planets are not communicating, yet they remain in step. A solar system can become a clock, not because it is rigid, but because its many moving parts have learned how to keep time together. There are worlds whose transits arrive early because another planet pulls them. A transit is supposed to happen on schedule. If a planet crosses its star every 10 days, then the next dipping light should arrive right on time. But in some systems, it does not. The transit comes a little early or a little late because another planet is tugging on the transiting world and changing its orbit slightly. These transit timing variations are incredibly useful. They can reveal planets that do not transit at all, and they allow astronomers to weigh worlds through their mutual influence. What makes this so satisfying is that the method turns punctuality into evidence. A tiny delay or advance in a distant shadow becomes the clue that another unseen planet is there pulling from the side. We learn about hidden worlds not by seeing them, but by noticing that another world missed its expected cue. In astronomy, even being late can become a form of revelation. Some strange systems may once have been far more crowded than now. The planetary systems we observe today may be the survivors of much more crowded beginnings. Early on, many stars may have hosted additional worlds that later collided, were swallowed by the star, or were ejected into interstellar space. What remains can look calm, but the calm may be deceptive. A neat modern arrangement may be the residue of ancient instability. This idea gives systems a sense of lost history. A star with 3 planets today may once have had 5, 7, or more, with close encounters gradually removing the losers. Giant planets may have bulldozed inner systems. Smaller rocky worlds may have merged into larger ones. Some rogue planets drifting through the galaxy may be the missing members of such families. It is a powerful shift in perspective. When we look at the system now, we may be seeing only the final cast, not the full original ensemble. Every quiet orbit may hide a much louder past. A few planets may have collided, merged, or been swallowed entirely. Planetary systems are not always graceful in their youth, and sometimes long after they can become crowded arenas where worlds cross paths, clip orbits, and eventually crash. Some collisions may shatter both planets into debris. Others may fuse them into a single larger world, built from fire shock and molten wreckage. And in still harsher systems, a permit may be driven so close to its star that it is swallowed whole. This is not speculation born from drama alone. Our own solar system bears signs of ancient violence, and exoplanet systems can be even more unstable. A planet that exists today may be the surviving result of earlier destruction. Its orbit may have been cleared by impact. Its mass may hide the remains of the world it absorbed. That makes every quiet planet feel more layered. A calm present can rest on a catastrophic past, and the worlds we find may be the polished survivors of astonishing acts of planetary violence. Some alien worlds may be the leftover survivors of planetary catastrophes. Not every planet we discover is a pristine example of how planets are supposed to look. Some may be survivors, the battered remnants left after a system tore itself apart. The world might once have had nearby companions that crashed into it, were thrown away, or vanished into the star. It may have lost its atmosphere in a violent era. Its orbit may have been altered by forces that destroyed other planets entirely. What remains is not the original design, but the last standing witness. That idea gives exoplanets a kind of emotional depth. They are not always simply exotic. Some may be scarred. Their strange density, odd orbit, or lonely placement may be telling us that catastrophe already happened, and this world endured it. In that sense, a planet can be like a ruin and a survivor at once. The system may have forgotten the disaster, but the remaining world still carries its shape in silence. There are planets smaller than Earth that still glow with molten surfaces. Size does not guarantee gentleness and permits. Smaller than Earth may orbit so close to their stars that their surfaces remain molten, despite their modest scale. We are used to thinking of tiny worlds as dim, cold, and geologically quiet. These planets overturn that instinct completely. They may be compact rocky bodies with dayside temperatures hot enough to melt crust into glowing lava fields. A little world can still be a furnace if the star is close enough. That is part of what makes them so captivating. They compress extreme conditions into a small frame. Instead of a giant inferno like a hot Jupiter, you get a reduced rocky world blazing like an ember in the dark. Some may even lose material into space under that intense heat. A planet does not need to be enormous to feel overwhelming. Even a world smaller than our own can become a place where itself glows and the ground behaves like fire. Some rocky worlds may be younger than many animals on Earth. Planet formation is not confined to the deep past. Some rocky exoplanets may be startlingly younger than many familiar lineages of life on Earth. While sharks, trees, and insects trace their ancestry back through immense spans of time, the distant rocky planet may have only recently finished assembling from dust and impact that creates a wonderful reversal in perspective. We tend to imagine planets as ancient in biology, as recent yet. In some cases, the rocks under an alien sky may be younger than creatures on our own world. Such planets could still be cooling, still sorting out their crusts, perhaps still enduring the final stages of heavy bombardment. Their surfaces may be fresh in a geological sense, with little of the long-worn memory that ancient worlds accumulate. This makes the galaxy feel less static. New rocky worlds may still be appearing while old life continues here, as though creation is happening in parallel across time. A few strange planets are so young, they rewrite early planet history. Every time astronomers find a planet in an unexpectedly young system, they challenge the old timetable for how quickly worlds can form. Some planets seem to appear sooner than the cautious versions of theory once allowed suggesting. That nature may be able to build large bodies with startling speed. This matters because the early life of a solar system is chaotic, dusty, and short on patience. The gas disk does not last forever. The planet becomes large while the disk is still present. It changes what can happen next, from migration to atmosphere building to resonance locking. Very young planets are not just interesting on their own. They are clocks that reset the story of formation. They tell us that the first chapters of planetary history may unfold faster and more dramatically than expected. A strange young planet can force the whole field to rethink its opening scene. because it exists before theory feels fully ready for it. Some worlds orbit within stars, habitable zones. It's still seen deeply hostile. The habitable zone sounds reassuring. It is the region around a star where temperatures might allow liquid water on the planet's surface. But that phrase can be misleading. A world can sit in that zone and still be utterly hostile. If the atmosphere is too thick, the planet may overheat in a runaway greenhouse. If the star flares fiercely, radiation may hammer the surface and strip away air. If the planet is tidally locked, one side may roast while the other freezes. Unless the atmosphere redistributes heat well enough, oceans, clouds, chemistry, and magnetic protection all matter. The habitable zone is not a promise. It is a starting point that is part of what makes these worlds so fascinating. They sit in the right neighborhood while still refusing to become gentle. A planet can inhabit the narrow band we once hoped for, and yet remain a place where life, as far as we can tell, would face extraordinary odds from the very first moment. There are planets where habitability depends on clouds, tides, and atmosphere. On some worlds, the difference between possible habitability and complete hostility may come down to a delicate balance of planetary details. Thick clouds can reflect starlight and cool the surface. Tidal heating can warm a world that might otherwise freeze. An atmosphere can move heat from one side of a tightly locked planet to the other, softening extremes that would otherwise be fatal. Remove any one of these factors, and the same planet might tip into disaster. This is one of the most beautiful complications in exoplanet science. Habitability is not simply about distance from a star. It is about interaction. It is about whether the world can regulate itself, whether air, water, and heat can cooperate long enough to create a stable surface. That means some planets may live on the edge of possibility, their futures shaped by the thickness of clouds or the strength of the tide. A world can survive because several subtle systems happen to work together. Some ocean worlds might look gentle from afar and lethal up close. Seen from a great distance, an ocean world can appear serene, a smooth blue sphere with clouds drifting above a global sea. It is the sort of planet that invites hope at up close, that beauty may conceal deeply hostile conditions. The ocean could be hundreds of miles deep with no land at all, and pressures below that rise to unimaginable levels. The atmosphere may be dense, acidic, or rich in greenhouse gases. Beneath the upper water layers, high-pressure ice could trap the deep ocean away from the rocky interior, cutting off the chemistry many scientists think life might need. Storms could sweep unchecked around the globe. What makes these worlds so gripping is that they blur the line between inviting and dangerous. They resemble paradise in outline, but perhaps not in substance. A planet can look soft and life-friendly in silhouette, while hiding conditions far more severe than any sea, storm, or abyss our own world has ever known. A few strange planets may have skies permanently hidden beneath steam. Some planets may be so hot and water rich that their skies never fully clear. Instead of blue air above a sea, they may be wrapped in thick layers of steam, with the atmosphere itself becoming a hot, wet shroud. On such a world, water exists, but not in the gentle way we usually imagine it. Surface temperatures may be high enough to keep oceans violently evaporating, feeding a dense envelope that blocks any direct view of the sky. Starlight would filter down weakly through a heavy, humid haze. The horizon might feel smothered rather than open. These steam worlds are fascinating because they take one of the most hopeful planetary ingredients, water, and push it into a far more intimidating state. The result is not a blue sanctuary, but a pressure cooker. A planet can be water-rich and still feel profoundly hostile, its whole atmosphere turned into an endless boiling curtain between the surface and the stars. Some planets may never cool enough for rain rivers or stone. We think of rock as the solid baseline of a planet, yet some worlds may be so intensely heated that the familiar cycle of cooling and hardening never fully settles. If the star remains close enough and the temperature high enough, rain, as we know, it may never form. Rivers cannot persist, and the surface may never stabilize into ordinary stone across large regions. Instead, molten rock or mineral vapor may dominate the active face of the world. In a place like that, the usual stages of geology are interrupted. There is no quiet weathering of mountain ranges, no long carved valleys, no patient movement of water over rock. The planet stays too hot for those stories to begin. That is one of the most startling lessons of Strange Planets. Not every world gets to become familiar. Some remain trapped in a more primitive physical state, as if they are forever stuck in a chapter our own planet left behind long ago. There are worlds where gravity would make every movement feel completely alien. Gravity shapes experience more than we usually notice on Earth. Every step, jump, and fall unfolds within a familiar pool that our bodies learned from birth. But on some exoplanets, especially massive rocky super-Earths, gravity could be far stronger. A simple walk might feel like climbing, with every step lifting an arm could become tiring. Jumping would lose its upward freedom almost completely. On lower gravity worlds, the opposite would happen. Falls would be gentler, movement springier, and every motion slightly untethered. This matters because it reminds us that a planet is not only an atmosphere or a temperature, it is a physical conversation with the body. Gravity tells you how heavy your bones feel, how fast you tire, how a tossed stone arcs through the air. Some worlds may look broadly Earth-sized in a catalog, yet the lived sensation of being there would be utterly strange. Even the act of standing could feel like entering another kind of physics. Some strange planets may have days longer than their years on Earth. A day is much shorter than a year, so the rhythm feels natural. Yet on some exoplanets, the balance may reverse. A planet can rotate so slowly that one full turn on its axis takes longer than one complete orbit around its star. In other words, its day exceeds its year. This sounds impossible at first, but it is a real consequence of orbital and rotational dynamics. Under the right conditions, such a world would experience sunlight in a profoundly unfamiliar way. The star's position in the sky would evolve through a strange contest between the slow spin of the planet and the faster completion of its orbit. Time itself would stop feeling intuitive. The basic units that guide life on Earth would no longer align in any comforting pattern. This is one reason strange planets are so intoxicating to think about. They do not simply offer new landscapes, they rearrange the meaning of common words, including day, year, and the passage between them. Few planets keep the same face turned starward forever. Tidal locking is one of the most dramatic ways a planet can be reshaped by its star. Over time, gravitational friction can slow the world's rotation until one hemisphere always faces inward. That means the same landscapes receive endless daylight, while the far side never sees the star at all. The consequences ripple through every part of the planet. The hot side may build towering clouds or blazing deserts. The dark side may become a place of ice haze, or deep cold winds may rush continually between them, trying to redistribute heat. What is so haunting about this arrangement is its permanence. On Earth, no place ends the sun forever. On a tidally locked planet, half the world does. The star becomes a fixed feature of geography rather than a traveler across the sky. It is an astonishing form of stillness imposed by gravity, where day and night stop being times and become places. Some worlds may have twilight rings where temperatures stay strangely balanced. On a tidally locked planet, the region between permanent day and permanent night can become especially intriguing. This twilight band, often called the terminator zone, may hold the most moderate conditions on the entire world. Too far toward the star, and the surface overheats too far into darkness, and temperatures collapse. But along the narrow ring between them, heat and cold may balance in a way that creates more stable conditions that does not guarantee comfort. Winds could still be fierce, and the atmosphere may still be strange. If the idea is mesmerizing, a whole planet may reserve its most temperate territory, not in continents or hemispheres, but in a thin and cycling belt where dawn and dusk never end. Habitability, if it exists, could become a ring instead of a broad zone. A world might be mostly hostile, with only one permanent band of possible calm wrapped around it, like a line drawn between extremes. There are planets whose stars make their skies glow deep crimson. The color of daylight depends on the star around. Cooler red dwarfs. The light bathing a planet would be shifted toward longer wavelengths, giving the world a very different visual mood from Earth's blue-white sunlight. A sky there might not appear red in the simple way people first imagine, because atmospheric, scattering clouds, and chemistry all matter. Yet the overall illumination could still feel dimmer, warmer, and more coppery or crimson-toned than anything familiar here. Sunset colors might linger in the character of ordinary day landscapes, would take on a different emotional weight beneath that light. This matters because a planet is not only defined by surface and air, it is defined by the color of its star. The same mountain, ocean, or cloud deck would feel changed under a deeper red sun. A strange planet may not only be physically alien, it may be visually tuned to a different color of reality from morning onward. Some strange worlds may be better compared to furnaces than planets. At a certain point, the word planet begins to feel almost too mild. Some exoplanets are so hot, so irradiated, and so physically transformed by proximity to their stars that they resemble industrial furnaces more than places in the ordinary sense. Their atmospheres may contain vaporized rock or metals. Their daysides may glow with heat intense enough to melt crust. The winds may race at terrifying speeds above chemical conditions that no earthly weather system can match. Calling such a world a planet is correct, but it does not convey the experience the term now has to hold. These are not gentle spheres quietly orbiting a sun. There are active thermal systems on the savage energy input. The fascination lies partly in that mismatch. A familiar category stretches until it almost breaks. A planet can still be a planet, and yet feel closer in spirit to a forge, a kill, or a blast of contained stellar punishment than to any world we call home. A few alien planets may be more extreme than many stars. This sounds backwards because stars are supposed to be the truly extreme objects, yet some planets. Rival laws surpass certain stars in specific conditions. Ultra-hot Jupiters, for example, can reach deer-side temperatures hotter than some cool stars. That does not make them stars, of course, because they lack the mass and internal fusion that defines stellar life. But it does reveal how misleading our categories can become. A planet can be cooler than a star in general, and still outstrip many stars in the temperature of an upper atmosphere or surface conditions. That is a thrilling reversal. The word planet tends to suggest lesser intensity. These worlds refuse that role. They occupy a strange borderland where classification stays clear, yet intuition starts to wobble. Giant world can be blasted so fiercely that in the specific reality of heat, it becomes more extreme than stars we might otherwise imagine. As the hotter class of object, some distant worlds seem impossible until telescopes prove they are real. Again and again, astronomy has followed the same pattern. First comes the idea that a certain kind of planet would be too strange, too unstable, or too unlikely to exist. Then comes the discovery that nature made it anyway. Giant planets skimming their stars' worlds around pulsars, planets with densities so low they seem absurd rocky bodies with molten faces, systems packed tighter than theory once preferred. This is one of the deepest pleasures of the field. The universe keeps outgrowing the imagination used to predict it. Telescopes turn impossibility into data, and the catalog of known worlds becomes a history of corrected expectations. That is why strange panics feel so powerful. They are not only fascinating places, they are reminders that reality is larger than human comfort. Every time a world once considered unlikely becomes real, the cosmos opens a little wider, and our private sense of what is possible has to make room. Strange planets have turned the universe into a place of endless surprise. Before exoplanets were known in large numbers, it was easy to let our own solar system feel like the standard design. Rocky planets near the star giant ones farther out. A neat arrangement, familiar and seemingly sensible. Then discovery after discovery broke that confidence apart. Worlds hotter than expected, puffier than expected, darker than expected. More crowded, more lonely, more violent, and more inventive than the old picture allowed. That transformation is bigger than any single planet. It changed the character of the universe itself. Space stopped feeling like a place that probably repeated our local pattern with minor variation. It became a place of radical diversity. The lesson is both scientific and emotional. The cosmos is not merely large, it is imaginative in a way that feels almost mischievous. Strange planets have taught us to expect surprise as a baseline. The deeper we look, the less the universe behaves like a tidy extension of what we already know. The weirdest planets may still be the ones we have not found. For all the astonishing worlds already known, we are still early in the story. Our detection methods favor certain kinds of planets over others. We are best at finding large worlds close to stars or special systems align just right for our instruments. That means the catalog is not the full truth of planetary diversity. It is a first draft shaped by what current technology can most easily see. Somewhere beyond that bias may lie worlds even stranger than the ones that have already shocked us. Planets with combinations of chemistry, orbit, and structure we have not yet imagined. Systems built in ways that current theory barely hints at. This is what makes the subject feel alive rather than finished. Discovery has not narrowed the universe. It has made its hidden portion more tantalizing. The strangest planet may not be famous, yet it may still be waiting in the dark, untouched by our telescopes ready to overturn the picture one more time. Thank you for drifting through these strange and extraordinary planets with me. Tonight we've wandered far beyond the familiar worlds of our own solar system into a cosmos filled with metal rain, molten seas, wandering rogue planets, and skies lit by two suns. We've passed through worlds stretched by gravity, worlds hidden beneath steam, and worlds so hot that rock can melt, can rise into the air. With imagined deep ocean planets with no shore at all, dark planets that swallow light, and distant young world still glowing from the violence of their creation. And perhaps that is the most remarkable part of all. The universe is not only larger than we once believed, it is stranger, richer, and more inventive too. Out there beyond the reach of our hands, entire worlds drift in silence, each one carrying its own weather, its own light, its own long and hidden story. Some may glow like embers, some may sleep in darkness, and some may still be waiting for us to find them. But for now, you do not need to travel any farther. Let the stars grow soft in your mind. Let those distant skies fade into darkness. Allow your breathing to slow, and let the weight of the day slip gently away. You have gone far enough for one night. The universe will still be there tomorrow, vast and waiting, with all its strange and beautiful planets turning in the dark. And if you're still awake and you'd like to continue drifting with me, there will be another video waiting for you on screen. If you enjoyed this journey, you might like to subscribe, leave the thought below, or return for another voyage soon. It helps more wandering minds find their way here, one sleepy soul at a time. Sleep well and good night.